Okay, welcome back, ladies and gents, to topic 2.7, this time assigning hybridization to atoms. When we're looking at Lewis diagrams of atoms, you might be asked to assign the hybridization or determine the hybridization around one of the atoms in the Lewis diagram. And in order to do this, we need to follow two steps. First, we need to count the number of electron domains. An electron domain is considered a bond or a lone pair. Okay, so anywhere there's a bond or lone pair, we count that as an electron domain. Things to be careful though when you're talking about electron domains. You count double and triple bonds as one domain. Okay, so if you see a double or triple bond somewhere, you're not going to count 2 domains for a double bond or 3 domains for a triple bond. That whole double bond or whole triple bond is counted as one bonded domain, and we'll go over an example of what that looks like. Once you have determined or counted all of your domains, you're then going to assign the S and the P's in order, okay? And I'll show you what that looks like on the next slide. Okay, here is CH4, also known as methane, and here is the Lewis diagram for methane. Okay. And the question is asking us to assign the hybridization or determine what type of hybridization the carbon is going to have. So in order to do this, let's start by counting all of the electron domains around carbon. Okay. Now normally we would do this on our fingers, but since we don't have that ability, at least I don't have that ability to show you right now, we're going to count with numbers, okay? So the first electron domain is right here, this bond to hydrogen. That's one electron domain. There is another bond to another hydrogen right here that is so far 2 electron domains. There's another one right here, that's 3 electron domains, and then right here, 4 electron domains, okay? Now keep in mind, there is 1 type of s orbital and 3 types of p orbitals, okay? And we can either mix that s with 1 of those p's, 2 of those p's, or all 3 of those p's, okay? And we determine that by counting the electron domains, okay? So we're going to start with s. The first domain is obviously that s, okay? The second domain is going to be that p. The third domain is going to be another p. And then the last domain is going to be the last p. So in order to get 4 electron domains, we have to mix 1 s orbital with 3 p orbitals, which means we're going to have an sp3 hybridization around that carbon. Okay, so that we say that that carbon is sp3 hybridized. That carbon is sp3 hybridized. It's mixing 1 of its s orbitals with all 3 of its p orbitals in order to obtain all of those single bonds there. Okay, and remember, the single bond is called the sigma bond, and we do sigma with that lowercase delta right there. I'm sorry, that is the wrong way. Sigma looks like this. Sigma bonds. Okay. Alright, now let's look at a case where we have a double bond in question, okay? What is the hybridization around this carbon? Okay. Well, let's go ahead and go through our electron domains. There is 1 electron domain right here, that carbon-hydrogen bond. There is another electron domain right here with that carbon-hydrogen bond. And this whole thing right here, this whole double bond counts as 1 electron domain, okay? Not 2 electron domains for a double bond, but 1 electron domain. And remember, we have 1 type of s orbital and 3 types of p orbitals, okay? And we're going to go ahead and assign the orbitals in order from s to p with these 3 domains here. The first one is always s. Always s for the first domain. The second domain is going to be p. And that third domain is going to account for our other p orbitals. So, and we don't have any more domains, so this last p does not get assigned. We have mixed together one s orbital with two p orbitals, which means this is a sp2 hybridized carbon. Oopsies. So that carbon is sp2 hybridized. Make sure to include those lone pairs on that oxygen there. Okay. Now the question could follow up and ask you to determine the hybridization for this oxygen, but and it's the same process, but we won't get into that right now. Okay. Alrighty, let's take a look at our last example here. What is the hybridization on this carbon here? Okay. Well, let's go through and start counting our electron domains. There is one electron domain, let me use red. There is one electron domain here for that hydrogen. And then for this triple bond over here, that is another electron domain. Remember, we count double and triple bonds as one domain, not 1, 2, 3 domains. Only one domain there. And if we go back to what we knew before, there is one type of s orbital, and there are 3 types of p orbitals here. And we're going to go ahead and assign those in order based on the domains. The first one is always S. And then with our second domain, we have a P assigned. And there are no more domains, so these 2 P orbitals will not be assigned. Those 2 orbitals will not mix, they will be unhybridized. We have hybridized or mixed one s orbital and one p orbital to form an sp hybridized orbital. So that means this carbon right here is sp3 hybridized. And that makes sense because there's a triple bond in there. Now going back and assigning sigma and pi bonds, remember that the sigma bond always occurs with the single bond, okay? So there's a single bond right here, so that is a sigma bond, okay? Triple bonds are made of 2 sigmas, or 2 pi's and 1 sigma. The center one is the sigma bond, and the pi bonds are the 2 outside ones, okay? Let's go ahead and assign the sigma and pi bonds on this one, okay? Anywhere there's a single bond, that's a sigma. Okay, so there's a single bond, there's a sigma bond there and a sigma bond there. With a double bond, it's made of 1 sigma and 1 pi. For the double bond, it doesn't matter which one you choose as sigma or pi, you can choose either one. So we'll call this one the pi bond and this one the sigma bond. Okay. It does matter which one you choose when you do the triple bond. Okay, the center one is always sigma, and the outer 2 are always pi. Okay, and we'll get a little bit more into that when we discuss this during our synchronous session. Okay, go ahead and go through the practice problems of assigning hybridizations. The other example problems will include atoms other than carbon, but the process of figuring out their hybridization is still the same. Okay. We'll see you in the next video.